Now let's consider an impulse function and the Laplace of an impulse function. This is referred to as the Dirac delta function because it's named after Paul Dirac. Think of hitting something, striking with a hammer where you have a sudden force that's released, or maybe you have a car accident where you have a hit and then it bounces off. Or if you think of a lightning strike where you have a sudden voltage, a voltage spike that occurs and then is released. Now this is not like a voltage where we're going along at zero and then all of a sudden we had a constant voltage applied like we did with the unit step function. This is where you're going along at zero, you have a very large spike and then it's released quickly.
So let's look at a definition. The delta function is characterized by these two properties. It's zero when t is not equal to zero, and it's very large, we're going to say infinite, at t equal to zero. And the integral from minus infinity to infinity of f at t times the delta function is simply the value of f at the point this impulse is applied, t equal to zero. We don't have to apply it at t equal to zero, we can apply it at t equal to a. Delta of t minus a is zero when t is not equal to a, and very large or infinite at t equal to a. And this integral, now it's typically referred to as the sifting property, now this integral is the value of f at the point the impulse is applied, t equal to a. Now, delta of t minus a is not a function in the classical sense. It's actually a generalized function or distribution, but in spite of this, it's been used very effectively to solve physics and engineering problems, and we're going to look at its mathematical justification.
So here, the impulse is the area under this curve that we're talking about, the force applied over a short time interval. So we're looking at this over a time interval from t0 to t1. We're going to look at what happens as we take the t values closer and closer and closer to t0, and we keep the area under here the same, but the height gets larger and larger. So here's our heuristic argument. An impulse, the integral from t0 to t1 of this force dt, and of course a force is mass times acceleration here with Newton's second law. So here we are, mass times acceleration, but we're going to integrate that, and we want to integrate with respect to t. So we've got mass times dv dt, integrating over dt, so that's just mdv. So what we get here is mv evaluated at t1 minus mv evaluated at t0. So this impulse is nothing more than the change in momentum over that time interval. And it looks, again, what you see right here, we're going to take the time interval will be smaller and smaller. We're looking at t0 to t1, t0 to t2 is smaller, and then t0 to t3 smaller again. What we're going to look is eventually is what happens as t sub n approaches t0 here.
Well, let's go to a specific example where we have a hammer striking an object, transfers momentum to the object. The change in momentum takes place over a short time period, first, say t0 to t1. So capital F1 of t represents the force due to the hammer. The area under that curve is the impulse or change in momentum. If, as we just discussed, the same change in momentum takes place over shorter and shorter intervals, then the force must get bigger and bigger for the impulses or the areas under the curve to remain the same. So this area is the same as this area is the same as this area. So in fact, if those forces having the same impulse act over intervals t0 to t sub n, where now t sub n is going to approach t0 as n approaches infinity, then f sub n approaches a function that's 0 for t not equal to t0, but infinite or very large when t is equal to t0. So the areas have a common value. We're going to normalize them to be 1.
So we're going to keep the areas under these curves here, they're equal to 1 since we've normalized those. So we're headed for a smaller and smaller time interval and a higher and higher height here on this. And that's our delta function, which we said was, quote, infinite there. It's getting larger and larger there. So our limit as t sub n approaches 0 of the integral from 0 to t sub n, f of t dt. That's a function, delta t, that satisfies this relationship. It's 0 for t not equal to 0, or it's infinite at t equal to 0. And later we'll talk about more generally being t equal to a rather than just t equal to 0. So if you're looking at this integral condition here, the integral from minus infinity to infinity is 1 because it's 0 up until you hit 0, and then it's infinite at 0 and stays 1 from there on. If you can remember the indeterminate form, 0 times infinity, where we had a limit that was 0 times infinity, and we could end up with any number there. Well, now we're looking at 0 times infinity of 0 times infinity. You notice we're keeping the area under that curve equal to 1. So we're actually looking at this indeterminate form, 0 times infinity is equal to 1 here, where delta is our infinite spike right here.
Well, now let's find the Laplace transform of delta of t minus a. We'll make use of the sifting property. For Laplace transform, the definition of the Laplace transform is the integral from 0 to infinity, but I can use the sifting property. First of all, delta of t minus a is 0 until t gets up to a. We're just going to replace, we can think of using this with f equal to e to the minus st. So this is simply f at a, which is e to the minus sa, or e to the minus as, for a greater than or equal to 0. A has to be greater than or equal to 0 because we're talking about a Laplace transform where t is greater than or equal to 0. So the Laplace transform of delta of t minus a is e to the minus as, again, for a greater than or equal to 0. If a is 0, it's the Laplace transform of delta of t is 1, and the inverse transform of 1 is delta of t.
And this is a very important relationship because up until now we've been unable to take the inverse Laplace transform of a constant. If you remember back to earlier semesters when we had calculus and we're dealing with partial fractions, remember if the numerator was of higher power than the denominator, you had to divide first, and you eventually got a constant out of that. Like if we had an s in the numerator and an s in the denominator and you divide, you get a 1, and you want to take the Laplace transform of that. Well, we were unable to do any problems like that back when we had inverse Laplace transforms and partial fractions. And now, with this relationship, we'll be able to work problems where we would have the inverse Laplace transform and the s in the numerator of a polynomial is of the same power or higher power than that in the denominator. And what we're going to look at here is the relationship between the delta function and the unit step function. Remember the integral from 0 to t, delta of x minus a dx, it's equal to 0 up until t is equal to a, and then it stays 1. Remember the area under the curve is 0 up until we get to a, and then it hits up to 1 at that point. So if we think of the fundamental theorem of calculus, now we don't actually have a function here. This infinite jump is not actually a function, but if you think of the first fundamental theorem, and as our textbook said, the spirit of it, we've got the derivative with respect to x of the integral from 0 to x, f at t dt. And what we do with the fundamental theorem there? Well, we could find the derivative simply replacing this t with the x that you see right here, and we got f at x. So if, instead of the derivative with respect to x, if we have the derivative with respect to t of delta, a function x minus a dx, we can replace the x here with the t, so we have the integral of that is equal to delta of t minus a. So the integral of from 0 to t of delta of x minus a dx was the unit step function. Remember, we were 0 up until we got to a, then 1 thereafter. So that's the unit step function. So we're really taking the derivative of the unit step function here, and what we have is that's delta of t minus a. Again, this is not actually a function, and U, of course, is not a continuous function. It has a jump discontinuity there at t equal to a.
So our objective asks us to solve some problems involving this Dirac delta function.
It can be difficult to solve a differential equation that involves an impulse function without using Laplace transforms. So that's what we're going to do now. In the next unit, we're actually going to develop a spring mass system in simple harmonic motion. Right now, we're just going to give you a differential equation that involves that. What we have is a spring mass system, and we have a mass that's attached to a spring, and it's attached to a fixture, and we're going to pull that mass down and release it, and it's going to start to vibrate in simple harmonic motion. And then we're going to hit that with a hammer, which gives us an impulse function, and we're going to see how that affects it. So let's take a look at this problem. It says a mass is attached to a spring, is released from rest 1 meter below equilibrium. Actually, we're going to take downward as positive, so that's going to be a plus 1 meter. And it starts to vibrate. Then after t equal to pi seconds, the mass is struck by a hammer. And what we want to do, we have a differential equation that looks like what you see right here. Actually, this left-hand side comes from the mass itself and the spring constant, and the right-hand side is called a forcing function, and the forcing function here is an impulse function. And we're considering that now while we're talking about impulse functions. Now, as I said, at time t equal to 0, we pulled that down 1 meter, and that's positive. And so we have y at 0 is equal to 1. And it was at rest, so it's released from rest. So y prime at 0, it has no velocity. Y prime at 0 is 0.
We're going to solve this differential equation using Laplace transforms. So taking the Laplace transform of both sides, we have Laplace transform of y double prime plus 9 times the Laplace transform of y is the Laplace transform of 3 delta of t minus pi. The Laplace transform of the second derivative is s squared, capital Y at s, minus s y at 0 is 1, minus y prime at 0, which is 0. Plus, then we'll have 9, capital Y at s, and on the right-hand side, we'll have 3 e to the minus pi s. I need to solve for capital Y at s, so notice I can factor on the left-hand side. I've got an s squared plus 9 times y at s. I've got a minus s, but it's going to come over to the other side, so that here is capital Y at s. We're going to break that up into these two pieces. This one we read directly out of the table. That's the Laplace transform of cosine of 3t. This one is e to the minus pi s times the Laplace transform of sine 3t, which is 3 over s squared plus 3 squared. So I can use this formula that we have, the inverse Laplace of e to the minus as, capital F at s, is f at t minus a, u of t minus a. So we have finally the solution to our differential equation. Y of t is cosine 3t plus u of t minus pi, because a is pi, sine of 3t minus pi.
Here we have a graph of this motion, and notice the change in amplitude from what you would have if you didn't have the impact, and also you have a phase shift here. Let's look at another problem involving an impulse function.
We're going to use the sifting property as we look at another example of taking the Laplace transform involving a delta function. The Laplace transform of delta of t minus pi times cosine t is the integral from 0 to infinity, e to the minus st cosine t, delta of t minus pi dt. So the f of t, as we go to use the sifting property, is e to the minus st cosine t. So we will evaluate that at t equal to pi, which gives us e to the minus s pi times cosine pi, which is minus 1, or the result is minus e to the minus s pi. In general, the Laplace transform of delta of t minus a times f at t is the integral from 0 to infinity, e to the minus st f at t, delta of t minus a dt. So we're going to have this evaluated at a, which gives us e to the minus as f at a.